Good day, this is Jim Pytel from Columbia Gorge Community College, Renewable Energy Technology Program. This is Digital 1 EET 121. Today we're going to discuss binary digits, logic levels, and digital waveforms. So every time anyone hears the word digital, they inherently think it's something very high-tech, and I'm here to tell you, no, it is not high-tech. This is the inventor of the digital system, Og the Caveman. Basically, what he has is a situation where he's creating smoke, no smoke, smoke. There exists two possible states: smoke, no smoke, smoke, no smoke. You could think of this as Morse code, as a dot, dash, dot, dash, but in our particular case, we're using high and low voltage waveforms. Okay, so there's two different states: high, smoke, low, no smoke. Not very high tech. Okay, so a code is a combination of binary data used to represent a number or symbol or information. So combining our highs and lows, we can come up with a code to represent the number 6 or the color blue, something like that. Like, for example, Og's smoke, no smoke. Smoke may mean come on over, since he's using a code. Okay, so I use the term bits. A bit is a binary digit. In our particular case, since we're using states of high and low, we have two binary digits, 0 and 1. And typically folks use positive logic, where a high is a 1 and a low is signified with a 0. Negative logic, it's opposite. So that's positive logic. Negative, obviously, opposite. So we don't necessarily use negative logic. We're going to use positive logic, where a high is a 1, a low is a 0. Okay, so the logic levels, since we're using, in our particular case, voltage levels, so we have to basically figure out what a 1 means and what a 0 means. Okay, so for TTL logic, we're going to use plus 5 volts is a 1, and 0 volts is a 0. Okay, so that's in an ideal world. In an ideal world, every 1 is exactly plus 5, and in an ideal world, every 0 is exactly at 0 volts. We don't live in an ideal world, and there's going to be some slop one way or the other. So for a TTL circuit, I'm going to go ahead and draw a graph here. And here's a graph of what TTL would be. Ideally, if we had a waveform, or if we had a logic value of exactly 5, we know it's in the high region. If we had a waveform exactly at 0, let's put that a little bit more exact. Exactly at 0 right there, we know that that waveform exactly is within the low range. So like I said earlier, there is a range. Okay, and the range for TTL logic is anything between 0 volts and 0.8 volts is considered a low. So even if our value is right here, let's say at 0.2 volts, we would consider that's acceptable low. Now the value for a high, the ranges for a high, anything above 2 volts to 5 volts, that's considered a high. So let's say we're here at 4.6 volts, we're within the high region. So we can safely say that we are a high logic level. Okay, so notice this huge band in the center. This is an unacceptable or an invalid region. So let's say we have an example of 1.5 volts. We don't know if it's within the high or the low. Okay, so these are values that we're not going to use. Ideally, we're not going to be using these because there's no way for our circuit to tell whether we're in a high region or a low region, whether 0 or 1. So again, we're just not going to use voltage values within the invalid range. Okay, so in a digital waveform, basically, if this was a graph of time right here, all a digital waveform is as time progresses from left to right, our waveform changes values between high and low. So between 0 and 1, it's definitely low. Between 1 and 3, it's definitely high. 3 and 5, definitely low. 5 and 7, definitely high. Okay, and now as sloppy as these waveforms look like, what they're trying to symbolize is basically an ideal waveform. And an ideal waveform really, this is what you really want. An ideal waveform looks like this, where you have these very snappy, almost instantaneous transitions from regions of low to regions of high and back to low and back to high. The key point being these instantaneous transitions between states. It goes from low on this side, immediately transitions to high, and here immediately transitions to low with no in-between state. And again, we are dealing with a reality where it's significantly different than our desired result here. So we're going to have a non-ideal pulse. A non-ideal pulse is going to have a transition period, and it's going to look something like this. So again, this axis below here is time, and let's say we start off in a low condition. It's going to slowly creep up to a region of high, and it's going to slowly creep down. And sometimes you'll get pulses that look like this, where that's the transition from low to high, and transition from high to low. This looks very similar to a charging for a capacitor and a discharge for a capacitor. But with both of these waveforms here, what you'll immediately notice is this transition region. That is not a that is not a tiny region of time where you are in this invalid zone. Okay, so you need to be aware that there is a real pulse does have a transition time, TP-LH. Time for the pulse transition from low to high, and conversely, TP-HL. Time for the pulse transition from high to low. Okay, so these things are referred to. This is our rising edge, and this is our falling edge or trailing. Also referred to, respectively, positive edge and a negative edge. Okay, so one thing I neglected to mention in this here with our range of accepted values here, notice how our range for our low goes from 0 volts to 0.8 volts, and our range for our high goes from 2 volts to 5 volts. What do you think of this right here? If I had a logic here that my acceptable values were from 0 volts to 3 volts for a low and 2 volts to 5 volts for a high, so anything between 0 and 3 is a low, Anything between 2 and a 5 is a high. Can you see the problem that's occurring here? What happens when it's between 2 and 3? Well, according to this definition here, it's a low. But according to this definition, it's a high. Okay, so you need to have a region, a no man's land, basically, in between your highs and lows. So this one is clearly high. This one is clearly low. And again, for a practical circuit, these waveforms do have a transition time that is measurable. And your job is to make sure that that transition time between low to high and high to low is as minimum as possible. Okay? And TPLH, TPHL, these are all things on a data sheet that you'll see. And we're going to be doing data sheets on our labs, basically how to read a data sheet and exactly what those individual characteristics mean. One thing you'll also hear these referred to is basically this is our rise time. And again, think about it, it's going from low to high, it's rising, rise time. And now TPHL, it's falling, that is our fall time. The faster the rise time, the faster the fall time, the better. So given these two digital waveforms right here, what can you use to describe them? Well, your first thing that comes to your attention, this seems to be very regular, where this seems to be somewhat random. Okay, so a regular waveform which repeats itself every certain number of seconds, this is a periodic waveform. And same formula we used in EET 112 when describing AC waveforms, where the period is the length of time it takes for the wave to repeat itself. Same thing here for a digital waveform, and the frequency is the inverse of the period. So again, what is our period? It's the time it took for one complete cycle. Let's say this was, let's see, 1/60th of a second, or 16.67 milliseconds. What is the frequency? Frequency is 60 hertz. Whereas a non-periodic waveform, there is no natural frequency. It is taking the value, the digital value between 0 and 1, or 0 volts and 5 volts, as to whatever the code requires of it. Okay? A periodic waveform, this is referred to as a clock. And clocks are very important in digital systems because they are used to synchronize the activities of everything. We'll talk about how clocks are important a little bit later. But right now, this non-periodic, this is often represented, this is information. And that's your codes that are being transmitted. So what is non-periodic information? Something that's gathering data about like wind speed. You know, it's sending this data. Music, that's non-repetitive information, unless it's REM. That's very repetitive. So this is the information that's being sent. A periodic waveform, that's a clock. Okay, so what is the duty cycle of this clock? This is something you may not be familiar with in EET 112. Well, a duty cycle is, just think of it simply as the time it's on. Okay, so if it was 1/60th of a second between the full cycle, how long is it on, how long is it off? Well, it should be 8.3 milliseconds on, 8.3 off. So think about it, is it's working half the time. Okay, so time on, time for the period, time 100 times 100%. So time on divided by the period times 100%. In this particular case, 8.3 divided by 16.6 milliseconds times 100%. That's a 50% duty cycle. So now let's draw this wave and see if you can figure out what the duty cycle is, the period, and the frequency. So here we've got a wave that is repeating itself every 16.6 milliseconds. So frequency, 1 over the period, that's also 60 hertz. So wait a second, this is 60 hertz, and this one is 60 hertz? Well, yes, it's repeating itself every 16.6 milliseconds. So there's still 60 hertz, but the difference between the two waveforms lies in their duty cycle. So this one was on for 8.3, off for 8.3. So it stands to conjecture 50% duty cycle. This guy's on 5.5 milliseconds of every 16.67. So what's the formula for duty cycle? 5.5 milliseconds divided by the period times 100%. What's our duty cycle? Almost 33%. Okay? So now what if we were to take the perfect inversion of this wave? Basically, when it's a high, it becomes a low. When it's a low, it becomes a high. Well, the period repeats itself still every 16.6 milliseconds. And the time it's on high, 11.1 milliseconds. It's still 60 hertz. But what's the duty cycle now? It's 66%, meaning it's on 2/3 of the time, as opposed to this one being on 1/3 of the time, as opposed to this one being on 50% of the time. Okay? So period, frequency, duty cycle. You should be very comfortable at calculating these. Okay, a digital waveform, again, it carries information, and the bit time is defined by the clock, okay? So given this clock waveform right here, and we've got a waveform A that looks like this. What value is A taking as defined by the clock? Well, just break it up in intervals for the clock. And what does A read during that particular period? Well, A reads a 1 because it's high. This cycle here, A reads a 0, a 1. The next bit time is also a 1, and that's a 0. What we've just drawn here, where we're comparing the time relationship between two signals, this is a timing diagram. And this is very important to your understanding of digital systems. Basically, all it's doing is showing the simultaneous values, the simultaneous digital waveforms of 1 to 2 to 10 different waveforms, and the values that they take at an interval of time. Just think of this as, again, as multi-instrumental sheet music. Player A is playing such and such a tune at the same time clock is playing such and such a tune, okay? So what if the clock suddenly started playing notes every 16th note as opposed to every 8th note? And again, keeping to our sheet music diagram. Well, basically you're sampling signal A at twice the rate that you were previously. So the values you get here, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0. It's still the same signal A, but we're just sampling it twice as fast with a clock of half the period. Again, so you should be able to translate, okay, I've doubled the period. Have I increased or decreased the frequency? Well, it's taken longer to go if I've doubled the period, so I've halved the frequency. And then in our particular case, we've halved the period, so we've doubled the frequency. So this is half period, so we've 2 times the frequency, and hence we're sampling signal A twice as fast as we did previously. And again, timing diagrams critical to your understanding of a digital circuit. You can determine the state of any waveform relative to others at any point. Okay, so given a sample timing diagram that looks like this, we've got signals A, B, and C simultaneously displayed on this single timing diagram with a clock. What is the bit time where A and B and C are simultaneously 1? Well, at bit time 1, which is this bracket in between here, A is taking the value of 0, B is also a 0, and C is a 1. Bit time 2, between here and here, we've got 1, 0, 0, and bit time 3. Now that's where we're looking for. All are simultaneously 1s at bit time 3. So data transfer. Data is groups of bits that carry information. And let's say, for example, A, B, and C are waveforms here. That's data, that's valid information that we want to convey somewhere. And it doesn't do a lot of good if it's just sitting there, so we need to transfer it. Okay, there's 2 different ways to transfer data. And just think of a long line, long single file line trying to enter a building through a single door. And that's what's called is serial transfer, where A and then B and then C are being fed into a single door. With the advantages of this one, it only takes 1 wire to get you there. The disadvantage, very slow. Single line, but very slow. Okay, parallel as opposed to serial, think of 3 doors to a building. And A and B and C are simultaneously entering the building. The advantage, much faster. Disadvantage, requires more hardware. Basically, it's going to require 3 lines. So if it took us 1 second to transfer a single bit, how long would it take for A, B, and C to get in if they were using serial? Well, it would take you 3 seconds. Bit A took 1 second, B 1 second, C 1 second, and you used a single wire. How long does it take for a parallel communication, though? Only takes 1 second, because each individual bit is being simultaneously transferred in parallel. Disadvantage, we've got 3 wires as opposed to 1. Okay, we are going to go on to some basic intro to logic operations.